Hello, my name is Tyler Johnson. I am a graduate student at the Case Western Reserve University in Dr. Don Taylor's lab. I will be sharing my work on improving reaching with functional electrical stimulation by incorporating stiffness modulation. Functional electrical stimulation, or FES, provides a way for otherwise paralyzed individuals to move their own limbs despite not having a neural connection between the brain and the muscles. This is done by using electrodes to activate the muscles in a controlled way in order to complete desired movements. This restored mobility can drastically enhance the quality of life for these individuals, allowing them to again complete basic tasks of daily living. Because FES technology continues to evolve, new aspects of control are becoming relevant that have previously been largely overlooked. Specifically, my research focuses on the concept of limb stiffness or impedance, which is the result of simultaneous activation of an antagonist muscle set, and how this can be incorporated into upper limb FES control. While muscle activation that causes movement can be visually observed by the user by watching their limb, so long as their arm is clearly in view, other more complex dynamics, such as limb stiffness, may remain a mystery as there is no visual feedback for the user and no sensory input from the muscles. Despite limited feedback of muscle stiffness, it remains an important parameter for FES control. If stiffness is too low, this results in sloppy movements that are unable to acquire a target. If stiffness is too high, this makes for rigid movements and leads to fatigue and battery drain. The goal of this study is to determine a method for effectively modulating limb stiffness. Rather than thinking about stimulating certain muscles, we think about moving our arms towards objects, and the needed muscles are activated to accomplish that goal. In the same way, FES users utilize their brain signals to control limb movements, which are functions of predefined muscle activation templates. These templates represent a conversion from limb position to muscle activations. For example, as shown here, if the user thinks about rotating their arm outwards, the triceps might activate while the biceps relaxes. However, it's possible to hold your arm in the same position with varying levels of muscle stiffness. In this study, instead of using one muscle template for each movement, we used a suite of templates representing different levels of limb stiffness. Furthermore, we dynamically switched through these templates throughout the movement, enabling different stiffness levels at different points of the movement. The entire closed-loop process is shown here for the elbow joint. Using the previously described suite of muscle activation templates, and a simulated virtual user with two sets of antagonist muscles that can be used to rotate the elbow and shoulder joint in two-dimensional space, we were able to test various ways of modulating limb stiffness throughout movements and find the most effective method. Specifically, we chose to modulate stiffness as a function of decoded intended velocity and its derivative, a signal that's already obtained for control purposes. The equation shown here describes the stiffness level of the limb as a function of a constant, the decoded intended velocity, and the intended acceleration of the limb, along with the coefficients for each term. These coefficients represent how much each term should contribute to the stiffness modulation and describe the way that the stiffness should change throughout a movement, as shown in the figures, which is what we hope to discover from this research. Many 8-target center-out simulations were performed for all sets of coefficients, and the results were evaluated in terms of average time to target, path length, and energy usage, as determined by cumulative muscle activation. We found the optimal modulation equation shown here. These dynamic modulation results are shown compared to the optimal level of limb stiffness if only one constant level were to be used throughout the entire movement. The results indicate that even a simple dynamic modulation equation is able to significantly improve the movement quality in terms of path length, time to target, and energy used. These results are intuitive, as it makes sense for less stiffness to be used at the beginning of the movement and more stiffness to be utilized as the user approaches the target. We believe that these results can be generalized to more complex 3D models, and the overall success of dynamic stiffness modulation would still persist. Furthermore, this approach is valuable as no additional information need be collected beyond the typical control signals used to move a limb. I'd like to give a special thank you to Dr. Don Taylor for her role in this work. Also, this work was supported by NIH funding as listed. Thank you.